from the Universidad de la República, but he studied his PhD in France at the École Normale, and then he did a postdoc at Caltech in the US. So he's comes from the other side, from the math and signal processing side of the thing. So it's going to be interesting to see the concepts.
Hi, so I changed the title of my talk. Actually, the second talk has the title, the original title. So the first talk is going to be quite basic, an overview of different models that we generally use in applications of the formation process of images. So if you think it's too basic, tell me, and then I can start skipping or going faster, okay? So the agenda for the first talk is as follows. So first I will show a model which is used a lot in computer vision, in 3D reconstruction, etc., which is a geometric model. And for that we need some basic tools of projective geometry. We need to define planar homographies because images are a transformation from the 3D world to the 2D world. But we're going to see what happens when it's particularly interesting when we observe a plane. So planar homographies are important. And then we're going to derive a model which is called the pinhole model that you've probably heard about many times. And we'll see what happens with geometry when we put lenses. But all that at a very superficial level, okay? And then I'm gonna step inside the camera, and I'm gonna see what are the transformations that happens to an image when it goes from when it first reaches the aperture, and then it goes to the capture, to the CCD array, to the captured image. So there we have many things operations that can be modeled as linear, and this will define the impulse response of the camera, which is called the point spread function. We'll see some. I'll mention some effects that are not well modeled by these steps of modeling that I'm gonna present. This is a motivation for the second talk, actually, because we're gonna use it. We're gonna model the camera as a black box, okay? And then we'll see what happens when we are dealing with digital cameras. So we'll have sampling on the image plane, and this will have aliasing. Actually, cameras have aliasing. So I'm gonna talk a little bit about that. So first, how can we represent points and lines in the same, more or less in the same framework? Okay. So this amounts to working with homogeneous coordinates. So if we're given a point in the plane, we can represent a line by its three coefficients ABC, and but this correspondence is not one-to-one. Any constant times this vector gives the same representation. So if we work with the equivalent class of these vectors, these proportional non-null vectors, we have what is called the homogeneous vector that represents a line. The set of all these equivalences. So the set of this class of homogeneous vectors defines what is called the projective plane. And if we have a point, to represent a point in homogeneous coordinates, we'll have the following. So we say that we have that a point belongs to a line represented as before in homogeneous coordinate if these equations there, the line equation is holds. So the homogeneous coordinate of a point is just extending it by another coordinate, which is a constant, okay, non-zero constant for the moment. Again, any proportional vector gives the same representation, so we take the equivalence class of that, and all these vectors represent the same point, xy. So now, points can be represented by this vector, and we can go from homogeneous vector to the points in the plane by normalizing by the third coordinate and taking it off, okay? So why is this representation interesting? First, because it makes computations very simple. So if you work with homogeneous coordinate, you have that a point belong to a line, a point x belongs to a line if you have this equation. You have that two straight lines intersect in the cross product of their homogeneous representation. And also you have that a line that goes through two points x and x prime is given by the cross product of the homogeneous coordinate of the points. So you can verify this. This is very easy. It's just linear algebra, and but it's very practical. One of the interesting parts of that is that it's very simple to prove that two parallel lines intersect at infinity. Okay? You take the cross product of the lines, and then you get a vector which has a zero third component. So what happens when you normalize by this third component? It goes to infinity. Okay? But it goes to infinity in a direction which is given by the coefficients of the line, by AB, so by the slope. So B minus B over A. So this give us direction. So points at infinity can be seen as directions. Okay? So finally, finite points in the plane are those that have a third coordinate which is non-zero, and then the others are point at infinity, and by completing the R2, extending R2 with these points at infinity, which are directions, we have which is called the projective plane. So now we can work with now we can define homographies in a very simple way. So first, geometrically, what is a planar homography? It's just a transform that preserves alignments, and it has to be invertible. So if we're given 3 points which are aligned, and we apply an homography, they have to be aligned. There's an algebraic definition that comes from working in homogeneous coordinates, which says that an homography can be represented by a matrix, a 3x3 matrix, because we are in R2 from R2, but we have to add one dimension for the homogeneous coordinate. So these are 3x3 matrices, which must be invertible. And an important thing to notice is that these matrices are defined up to a scale. Because if we multiply this matrix by a scale, then when we do the normalization by the third coordinate, we get exactly the same transformation. So these are homogeneous matrices. And these matrices then, instead of having 9 degrees of freedom, they have 8, because we have the scale factor. So if we want to determine H, it's very easy. We need 4 point correspondences in general position, so 3 of them shouldn't be aligned. And we have to put a constraint, and that's it. There we have the 9 equation, the constraint plus 2 coordinates per point. We can use finite points, or we can use vanishing points, because vanishing points at infinity are points for us, so it's the same. So this is a way that usually that people use to rectify images. When you take a snapshot of a painting and you want to transform it, well, you use vanishing points because you know where to place them. If you have more points, you use least square procedures. So you you have more equations, you use a least square procedure, and you have a more accurate solution. But it's linearly square, so it's very simple. So now we go to the pinhole camera model. Here I use this presentation, which makes things simpler. I've never used this, so I don't know how to turn it. How do I turn it? Okay. I can destroy my laptop. Yeah, then just to switch. Okay, yeah, maybe that. Okay. So when you take an image of an object, actually the image is reversed and goes through the optical center. Okay. So here what we do is we just symmetrize the plane, the inverted image, which should be here to here, and we don't have the inverse image. Okay, so this is just for making computations easier, because the geometric relations are going to be the same. So, this camera, what it does is to map points in 3D to points in 2D. So we have a point in 3D, MC. We take its homogeneous coordinates, so we have a 4D vector, and then we take the line that goes to the optical center, and you can easily see that the point M is given by this relation. This comes from here, okay? So this is YC, the height of MC, and then since this distance is F and this is ZC, so you have this height which is FYC over ZC, the same for the X coordinate. Then you have to translate M, because usually the reference frame on an image is not at the principal point, it's somewhere else. So the principal point has coordinates x0, y0 in the image reference frame. So you get this. This you can also transform it into homogeneous coordinate. You just multiply by a non-zero constant, and I chose to multiply by ZC, which I know is non-zero, and then I get in homogeneous coordinate the transformation, which writes this way. So we have this matrix, which this can also be simplified in this way. This matrix is very important because we're going to operate on this matrix and we're going to derive what is called the calibration matrix. So the matrix that characterizes my camera. So now MC was defined in the reference frame of the camera. If I have a fixed reference frame somewhere else, which I call the world coordinate system, we have a rotation translation to register these two frames. So we have this transformation to put the point in this world coordinate system. So I end up with this. Okay? This is intrinsic to the camera. This is the position of the optical axis. This is the focal length, and this is extrinsic. Depends on the position of the camera. So now in digital cameras, what happens? Units are expressed in pixels. So we have to know what's unit length of a pixel, and it doesn't need to be the same in X and Y directions. So these numbers, AU and AB, are the number of pixels per unit length in each of these directions. And then to transform to pixel coordinates, I just have to multiply by this matrix. And this is what I get. So this parameter here, AUF, what is it? It's the focal length in pixels on the horizontal direction, and this is the same in the vertical direction. Focal length in pixels. This is the principal axis position in pixels, And now everything is in pixels here. So I'm almost finished with this model. The only thing that I have to introduce is this coefficient here, which is a shear factor. So what does it mean? It means that the CCD array, the pixels in a CCD array, doesn't have to be perfectly orthogonal. Sometimes they are not. So I have to put a shear factor here. I will put it to 0. It's often very close to 0. But if you want to make a general model, you have to put it. Some grids, some sampling grids are not orthogonal, for example. And so this gives the calibration matrix. This characterizes my camera. This has to do with the focal length and the unit length of a pixel, and this is the principal coordinates, the principal point coordinates. So this is what is used in vision, computer vision. Computer vision, when you have two cameras, you need to calibrate each of them, and then in order then to be able to know the relative position of one from another, this is called stereo calibration, and then you can triangulate and you can have the 3D. But you have to go through this step. So the pinhole camera is not just a model. Actually, you can implement a pinhole camera. Just make a pinhole in a plane, and then you capture the image. And the first cameras were built this way. The problem, what is the main problem, is that the aperture is very small, so we don't have enough light. This is the first thing. So the images are generally dark. The other problem of small apertures, you know well that you have diffraction effects. So you could think of making the aperture larger, but then you have out of focus because the rays disperse. They don't focus on the same point. So this is an example. This is a pinhole camera with different apertures. This is too large, so we have dispersions until we reach this point. So we start decreasing the aperture. This seems to be the best one. But if we keep on decreasing, we start having diffraction. Okay, so dispersion on this side and diffraction on this side. So that's why we need lenses. But lenses have their problems too, because they're generally introduced, at least in regular cameras. It's very, you can notice it very well. They introduce distortion, and distortion is mainly radial distortion, that's typically what you see in images. Even in high-end digital SLR cameras, you see distortion. In very good lenses, you can see distortion. Zoom lenses have distortion because they have this kind of radial distortion because they are built usually for a functioning point for some focal length, and then when you deviate from that focal length, you start having distortion, and you can see them. This is called the barrel distortion, and this is called the pincushion distortion. Okay, so you see here you see this. So in computer vision, this is generally the kind of distortion model which is used. The distortion that depends on the distance from the distortion center. And that's it. It's a radial function. Because that, for computer vision purposes, is accurate enough. So now I'm going to the second part of the talk. So now we forget the 3D world and we observe what's the transform that happens to an image that arrives at this plane and then get captured at this plane. This U here is the projection of the 3D world into the aperture plane. When I talk about aperture, I'm not talking about the aperture of the camera, the shutter. Okay, it's the aperture, the first aperture you see on the lens, on the objective. And then B is the image captured in the image plane, or which is also called retina. Here is where the CCD arrays sit, or the CMOS array. So the first assumption, so we're going to study the process that transforms an image here from here. So we assume that this system is linear and shift invariant, which is not. So it's really not the case, but locally we can model it that way. Why is not? Why this assumption is not true in general? Because, for example, I have shown you distortions. It means that the image doesn't behave. The camera doesn't behave in the same way in different locations of the image. Okay. So it's really not a linear shift invariant system, but locally this approximation is good enough. So then you must have seen this many times, that you can characterize the system by the impulse response, which is a convolution kernel. And in the case of cameras, it's called a point spread function. So there are many linear shift invariant operations that give H, the diffraction kernel, the out of focus kernel, and then you have a kernel which is given finally by the integration at the captor. So the first kernel, the first PSF term is the diffraction, and if you work under the Fraunhofer approximation, which basically means that the aperture is small compared to the distance between the aperture and the image plane, then, well, I will skip all this stuff, but you can see that the field, the light field of a monochromatic wave of wavelength lambda is something which is proportional to the Fourier transform of the indicator of the aperture, the indicator function of the aperture. So, as a first approximation, I'm interested in circular apertures. So, if I work in, if I do this change of variables to polar coordinates, this is very simple to compute. So, we have an aperture of diameter d. You have to use the Bessel functions, blah blah, and then you end up with a formula for the light field at the image plane, which depends on the size of the aperture, depends on the focal length, and depends on the wavelength of the monochromatic wave that arrives to the aperture plane. So the captors are sensible to image intensity, not to this. So this image intensity is the square modulus of this field. So this gives the kernel diffraction, the diffraction kernel, the first component of the PSF we are trying to model here. Okay? It has this shape, these J functions here. J1 is the Bessel function of the first kind and of order 1. So basically we have the shape of this here is J of x divided by x squared. So then if you see what, so this is a plot of the previous function. The first zero crossing is here, 3.83. So this gives a formula to compute what is called the Airy pattern, the radius of the current Airy pattern, which is 122 lambda f over d. And this is very important because this is really a measure of resolution. If you put two different points, sources, it will give you two different kernels, the same kernel at two different positions, and then the resolution has to do to the point, to how much you have to separate the points in order to see them separate in the image. And so the area gives this very real resolution measurement. So let's see what happens. So, and this is the kind of image you get. Okay. So what happens when B increases? So when B increases, we have lower diffraction. We know that. But we have higher dispersion of rays, which is not modeled here. When lambda increases, then we have higher diffraction. And the area gets larger. So this is the first observation that we will confirm with the PSF estimation technique I will talk about in the next lecture, which is that the area disk for the red channel, so we have red, green, and blue channels. The area disk of the red channel is larger than the one from the blue and green channels. Now we go to the next linear operation that gives the kernel component 2, which is out of focus, and this is given by the Gauss formula for lenses, which says that in reality points, they don't focus at F, but they focus at distance Zi, which is larger than F. And this is given by this formula. So we have a point at Z0 here, this is Z0, and doesn't get focused at F here will be F, but at F plus delta, or F minus delta. And so this gives the okay? And so one can check that if we are observing a sig which has constant depth, then the focus for a circular aperture is given by this current, which is basically a constant function in a circular. So it's basically an indicator of a circle weighted by this stuff here. So again, we can do an analysis to see how F, delta, and D influence on the defocus curve. There are other distortions that are not modeled by what I have seen up to now. First, we have aberrations, monochromatic aberrations, which typically spherical aberrations. They don't cross at the same point here. You can see the ray. So even with a monochromatic light, you have this kind of effect. This is called coma, and this is called astigmatism. I won't talk about that because I'm not a physicist. But these are just these aberrations that are not taken into account by the model I have talked about up to now. You have geometric distortions, which are due to the fact that you don't really have the light that when it goes through the center doesn't get deviated. And this gives on one side what is called the barrel distortion and the thin gaussian distortion I talked about up to now. These are very common geometric distortions. We have chromatic aberrations, and these are caused by the fact that lights with different wavelengths go through different paths when they go through the lens. Okay? So they focus at different points. So if you take a focal plane somewhere, an image plane somewhere, let's say to focus your blue channel, then you will have these two out of focus. for all these I'm mentioning here, there exist optical devices that correct them, that minimize these aberrations. And then finally we have this effect which is called vignetting, which is the consequence of the fact that when we go from the image center to the borders, the energy, the image intensity that arrives to the image decreases. Okay? So if you look at pictures, you will, this is exaggerated, but you will always see like a black corner which is darker. All corners will be darker, even with very good cameras. Finally, we have the digitization process, which consists in, so now we have the image that arrives to the focal plane. We have an array of CCDs there, and we have to see what these captors get, and then what the image, the captured image is. So basically, this is an integration of photon counts that hit the surface of the captor, of each of the captors in the array. So this can also be as a convolution with a support, with an indicator function of the captor, usually a square. So finally, we have the whole of the PSF, which is the composition of the capture kernel, the diffraction kernel, and the defocus kernel. This is sampled in a regular grid, and this gives us the digital image. But we have here this term, which is noise. Noise means everything which we couldn't capture by the model here. And this noise, what we call noise here, has many sources. One is the photothermal noise, which is usually modeled as Gaussian, Gaussian noise. We have quantization, because the image intensities in digital images are not in a continuum. We have bits, so usually you have, I don't know, 256 levels. And then we have the captors nonlinearities. So the response to the light is not linear in the captors. So now I have to talk about aliasing, because it's something I'm going to use in the next talk. So you all know this Shannon-Whittaker theorem that says that if you have a band-limited function and you sample at least the Nyquist rate, which is 2 times the maximum frequency of the signal, then you can get perfect reconstruction by using the sync kernels. So the same holds for 2D. It's these separable bases of sync functions, these sync interpolators. So, and this is true if so U hat here is the Fourier transform of U. And we assume that U has fast decay. This is just to make the mathematics work. So, so you can retrieve the continuous image from its samples in a regular grid if you sample it fast enough. So the band-limited condition is this. So U hat has to be within the minus pi over delta support, and then if you sample with frequency, with a rate delta, you get perfect reconstruction. This is really an equality. Okay? But the problem with the previous formula is you have an infinite summation here, and these interpolator, these kernels decay slowly, decay as 1 over x. And we don't have an infinite number of samples, so we have to cut somewhere. And if we cut, then we start having other kind of problems. But this can be mitigated if you use windows and all that things that are used in signal processing. The other problem is that when you are observing an image is naturally not band limited. Why is that? Because there are edges, and edges is a discontinuity, so it can't be band limited. So if you want to have a good quality image, you shouldn't blur the edges. That's very bad. Okay? But in order to make the image band limited, and in order to be able to sample it at a fast enough frequency to trying to have edges which are pretty sharp, you have to do a severe low-pass filtering. So actually edges get blurry. If you do a non-severe low-pass filtering, then you have aliasing. So what's a good way to go? So, usually manufacturers make a trade-off between image blur and aliasing. This is a way of having edges which are pretty sharp, but you have aliasing, which is something I'm going to talk about now. So, where aliasing comes from and what is aliasing? Aliasing comes just for it's a property of the Fourier transform that has to do with the fact that the sampling and periodization are dual operations with respect to the Fourier transform. If you sample, this combi is a combo, it's a combo of Dirac deltas. If you sample an image, then in the Fourier domain you have a periodization of the spectrum. If you sample it fast enough, so let's say V is this periodization of the spectrum of U. Okay, so V is this function, and V hat we see is the periodization of U hat. If you sample your image fast enough, you are in this situation. So this happens when the support of the image is in this range. So everything is fine. If you don't sample it fast enough, what you get is these superpositions here, which result from aliasing high frequencies from the original image to low frequencies in V. Okay? So if you are not in the sampling, in the Nyquist sampling condition, you have frequency components, get alias in the low frequencies, and you see these kind of things, while you should have seen this. Okay? So you see there's a high frequency component that gets introduced in the alias image as a low frequency component. So all this is introduction, and so these are the texts that you can use to, if you want to have more insight on these topics. Okay. The reason why I present this is because I need all this for the next lecture. Okay, that's it for the first text. So I don't know if you have any question, or you can make questions after the second lecture. Yeah?
I was wondering if you could put your slide number 30 again. I might have a question there.
Yeah?
So that first equation that you're showing, is that your definition of your H captor?
Yeah.
So basically, it's
You have to integrate light in a given domain.
right.
C is just the domain of the capture, that usually is square.
Okay, and U here is
U is the continuous image, the image that arrives at the aperture plane, No, sorry. Yeah, U is the image you get for it. So these are all they all commute because they are convolutions. So these operations commute, and so you can think of U, for example, if I haven't introduced the diffraction kernel and the autofocus kernel, you can think of U as, for example, this image here, the U here. This U there. Okay.
Okay, so U is the image.
Actually, this is not very clear. So you can think of U as a continuous image that arrives to the CCD array plane, to the image plane.
Right.
Okay, and then you have to sample it. In order to sample it, you have this grid that integrates light in little squares,
Right.
and the convolution kernel is going to be the indicator function of your cutters. So squares here. Okay?
Okay, so if we go back to slide 30 again. So the final equation, I mean, I
This
get
one?
that. You have
Huh?
that when it commutes, you have the different operators. One for the I don't know why the focus is separate from diffraction, I guess.
Well, you can put them together if you want.
Right.
It's just a way of understanding things because
And I guess
the focus has to do with the lens. Diffraction doesn't have to do with the lens.
and then there should be a convolution, right, between there, right in front of you.
Yeah, there's a convolution here.
You see,
Yeah,
right?
yeah, thank you. Yeah.
So, but I guess that first equation just bothered me because it's not a convolution integral, but yet you have the right-hand side is a convolution of two functions.
If
But
you
the
well,
left-hand
if
side,
this stuff is symmetric, then it's a convolution. Okay.
okay,
You can always write. I mean, for a symmetric domain, then this is a convolution.
C is the area of the pixel.
C is the domain of the pixel. Yeah.
so it's not in there, I guess. So you can rewrite that as an integral.
Yeah, you can
function.
rewrite it as a
Yeah,
convolution. It's an integration, so
Right.
in this domain you can write it as a convolution.
Right, so I agree with you. So it's written more like as a correlation. but
Yeah, maybe it wasn't my slides were not clear enough, but you can. So everything I presented here can be written as a convolution. So you have the convolution of the
The
original
final
image
image.
that arrives to your optical device, convolved by all these, then sample, and then you have some residual here that models everything that wasn't captured by my model.
Okay, thank you.
You're welcome. You had a question?
Yes, I just didn't understand why you have ABC to represent straight line instead of A and B. Like a straight line, it has A and B, like equation of the straight line.
No, it has A, B, and C.
Yeah, why C?
Well, C is has to do with the intercept.
Intercept.
A and B give you the slope.
But slope, you mean it's three-dimensional line?
Now, these are two-dimensional lines,
Yes.
which are represented as 3D vectors in homogeneous coordinates.
AB, okay.
Yeah, so it's just, if you look at the line equation in the plane, this. Okay, you always have C. If you don't have, if C is 0, it means that your line goes through the origin. So it has to do with the intercept. And that's why when I try to see what happens when two parallel lines, where they meet, where they intersect, I have C and C prime here. These are two parallel lines.
Okay, let's Let's have a short break and then we come back.
Okay.
5 minutes.